right, we're back. Now this is probably one of the nastiest ones we've seen. So let's take a look at one that aren't slightly as bad. Oops, sorry. Aren't slightly as bad here. So let's see here. This one, let's see, we want to take the second derivative. Not too bad to do. We take the first derivative. Remember, we're looking for concavity here. So we're looking for that second derivative. The second derivative tells us the shape of the graph. Is it going to be concave up or is it going to be concave down? How is the graph opening? And right here, if we take the first derivative, we get 2/3 x minus 1, and this becomes to the negative 1/3 times 1. Taking the second derivative, this becomes negative 2/9 x minus 1 to the negative 4/3. And again, it's times 1 because of chain rule, but we don't have to worry about that. So I can rewrite this one. Our second derivative becomes negative 2 over 9 times x minus 1 to the 4/3. There we go, to the 4/3 right there. Let me write that a little bit nicer here. Make it look a little bit more presentable. Make it look like, whoops, hello. Make it look like somebody's going to look at this and judge me. To the 4/3. There we go. And now we're going to go ahead and find our possible points of inflection. And remember, this is very similar to what we did. So we don't need those minus 1s there. This is very similar to what we did with the first derivative test. And that's going to give us the following. If I find my possible points of inflection, these are like our critical numbers for the second derivative, where the second derivative is 0 or d and e. And I can find them pretty darn quickly. Is there any place where the second derivative is 0? Well, there's nothing on top except the negative 2, and negative 2 can never equal 0, so I don't worry about that. That's a no-no. Where does the second derivative d and e? And that's the bottom. I really only care about the bottom here. X minus 1 equals 0, and I get 1. I only have one possible point of inflection. And now we got to test it, though. There's 1, our second derivative, our function. What does it make my function look like? This becomes, remember, negative 2 over 9x minus 1 to the 4/3. And if I plug something in like 0 here, I am going to get the following. The top is negative, but the bottom, because the top is a negative, oops, sorry about that. The top is a negative 2. But if I plug into the bottom, I'm going to get 0 minus 1, which is negative. I can take an odd root of a negative, so that's not the issue. The issue is the 4. The 4 is even. The 4 is telling me I'm taking that negative 1, I'm going to take it to a 4th power, and we should remember that a negative 1 to a 4th power is a positive 1. So the bottom here is going to be positive, which is now telling me that this is going to be concave down. Plug in something big like 2. Again, the top is still going to be negative, but the bottom is also going to be positive again. That's what this is telling me. The bottom's always going to be positive. So it's also concave down. So notice, there is no concavity change. There is no concavity change right there. Therefore, we can say there is no point of inflection. Concavity doesn't change, no point of inflection. So let's go ahead and discuss the concavity, of course. We can say F is concave down on the following domains, negative infinity to 1 or 1 to infinity, and that's because the second derivative is less than 0. Now notice soft brackets, always soft brackets. And F is never concave up, so I should write that down. F is never concave up. And that's because the second derivative is never positive on this one. This is just a lonely, sad function that's always concave down. All right, so let's take a look over here real quick. Okay, let's take a look over here real quick. So over here, we have a triggerlicious function. So when we take the first derivative, we would get cosine of 2x times 2. Taking the second derivative, we get negative sine 2x. Be careful, chain rule again, that becomes times 4. So when we're looking for our possible points of inflection, where does the second derivative equal 0? Well, that's just this. Hey, give me 1 second here, Jim. Oh, sorry about that. All right, so here we go. So we're going to try to find our possible points of inflection here. So finding out where the derivative is 0, we are just going to let the sine of x equal to 0. So I get negative 4 sine 2x equal to 0. Where does it not exist? Sine is always existing everywhere, so we don't worry about that one. Solving it, I don't worry about the negative 4. It just goes away. Where is sine equal to 0? 0, pi, 2 pi. But I want to go around a few more times. 3 pi and 4 pi. So when I divide by 2, notice I'm going to get 0, pi over 2, pi, 3 pi over 2, and finally 2 pi, my favorite mathematical wrapper. I should have restricted that domain more. So when I do my domain, sine chart, 0 to 2 pi, our second derivative, and there's f. I'm going to plug in pi over 2, pi, 3 pi over 2, and, not drawing the scale, 2 pi is at the very end there. Oops. We are plugging in our derivative, which was this negative 4 sine 2x. So I'm going to pick something easy for me. Over here, I'll pick pi over 4. And if I plug in pi over 4, well, the sine of 2 pi over 4, well, this becomes negative 4 sine pi over 2, which is negative 4. So I know this is negative, so it's going to be concave down. Positive, concave up, negative, concave down, positive, concave up. Trig functions want to alternate, so I'm going to use that to my advantage here. And then I can answer. We have POIs at x equals pi over 2, pi, 3 pi over 2, and that is because the second derivative, 1, is 0 or D and E, and 2 changes signs. That's what we want. We can say, when are we concave up? F is concave up on the domains pi over 2 to pi, or 3 pi over 2 to 2 pi, and that is because the second derivative is positive. I know it's messy. F is concave down. I am ready for a vacation after today. On the domains 0 to pi over 2, or pi to 3 pi over 2, and that is because the second derivative is less than 0. Oh my word, that is a nasty problem. So let's take a look at an even worse one. All right, last example for today. We want to find out where this function is concave up and concave down. The first derivative, I'm going to use quotient rule, low, d high, minus the top, x squared plus 1, d low, 2x over the bottom squared. Now, I am going to do a couple of things here. One, I am going to distribute. And if I distribute, that becomes 2x cubed minus 2x minus 2x cubed minus 2x all over this x squared minus 1 squared. Cancel, cancel, and I get negative 4x on top. All right, that's not so bad. Now, if I'm looking for the first derivative, that's a nice one to do. Let's take a look at our second derivative. Quotient rule. Low. Oh my gosh. Low x squared minus 1 d high times negative 4 minus high, it's a negative 4, so I'll make that a plus 4x d low chain rule 2x squared minus 1 times 2x all over the bottom squared. Now you might be thinking, man, that's really ugly. But just like we did up here, way up here, we're going to have terms that cancel. And we're going to take advantage of that. This goes away, that becomes a 1, and that becomes a 3 right there. And now I can distribute and simplify like we did for the last one example. That's going to become negative 4x squared plus 4 plus 8 16x squared over x squared minus 1 cubed. All right. If I clean up the top, I'm going to get 4 minus 12x squared over x squared minus 1 cubed. And now we're going to find our POIs. Oh, man. Possible points of inflection. Where does the second derivative equal 0? That's easy. 4 minus 12x squared equals 0. You solve it, you would get plus or minus 1 over root 3. Why didn't we restrict the domain here? Where is the derivative does not exist? That's going to be this x squared minus 1 equals 0. Students sometimes ask, why do we worry about this cube right here? Well, let's plug it in. If I take the cube root, I still just get x squared minus 1 still equals 0, and that's going to give us plus or minus 1. There's our possible points of inflection right there. All right, so let's draw a sign chart. Go big or go home. Negative 1, 1, negative 1 over root 3. Whoops, you know what? I'm going to redo this one because it already kind of looks kind of messy there. I already see myself running out of room. Negative 1, 1, negative 1 over root 3, positive root 1 over 3. F double prime and F. And here we get going. Plugging it into our second derivative, 4 minus 12x squared over x squared minus 1 cubed. I am going to use multiplicity. I am going to cheat. Now, we do have a slight problem, though. Right here and here, these are vertical asymptotes. I know that because if I go to the top here, this has a domain restriction. X can't be plus or minus 1. Those are vertical asymptotes. So I'm going to identify them. So what I'm going to do is I'm going to pick a number. I'm going to pick a number in the middle, 0. If I pick 0, the bottom is going to be negative, and the top will be positive, because 4 minus 0 is positive. So that's telling me that this is going to be concave down. Now, there is no multiplicity here, and all that means is that my signs have to change. If this is negative, this has to be positive. This would be negative. Now, if this was a 2, it would be positive also, but it's not a 2. Changing here, positive and negative. And again, if this was a 2, this would also be positive again, but it's not. And there's our answer. So let's talk about the POIs first. It's a tricky one. We want to say negative 1 and positive 1, but negative 1 and positive 1 are vertical asymptotes. Therefore, these are not POIs. Because what's the key word? It's point of inflection. It's a point of inflection. So if it's not a point, it can't be a point of inflection. So the only ones that will work are this plus or minus 1 over root 3, and that is because 1, the second derivative is 0 or D and E, and 2, the second derivative changes signs. Next, F is concave up on the following domains, negative 1 to negative 1 over root 3. See, this I can include concavity because it's a soft bracket. I'm not including the asymptote, but here we would have to include it. Or from 1 over root 1 over 3 to 1. And that is because the second derivative is positive. F is concave down on the following domains, negative infinity to negative 1, or root 1/3, I'm having a hard time saying that, negative root 1/3 to positive root 1/3, or 1 to infinity, and that is because our second derivative is less than 0. All right, we're done. I hope you enjoyed this video as much as I have. I'll see you all later. Bye-bye.